Let's go for it.
Okay, that's number 3. Yes, thank you, Lenka. I know, I just divide the number of pages by 10 and I get it. Okay. So today I'm going to talk about how to infer one direction of interest into, in a very high dimensional space. Typically a space of dimension n when n goes to infinity, and there is one direction of interest which is actually biasing the distribution of some data, and we would like to infer from the data this specific direction. So it's a problem which is useful both and which is encountered both in the unsupervised and the supervised context, and I want to address both learning context here today. So in the second lecture, I made a very detailed replica calculation. So I think what I'm going to do now is that I will build on this. So I won't do very detailed calculation anymore, but I will give you what are the similar points to what I've done and what are the differences, so that you have enough, I think, material to redo the calculation. And if you have any problem, I will be very happy to answer your question, right? Okay, so the first part will be unsupervised learning on one specific direction, and you will see there is a very deep and close connection to what we have done last week, which was the spherical spin glass model. The only difference is that we will go actually from a GOE matrix to a Wishart matrix that Julio introduced this morning. Okay, so let me explain the problem. By direction, I mean vector. It's the same thing. Okay, so suppose I have a n-dimensional variable, so an n-dimensional vector x, and I will consider a very simple distribution, which is always the same multivariate distribution I've considered already many times, rho of x here. If I have, and it will be proportional to the exponential of minus 1/2 sum over I xi squared. That would correspond to independent components here of my vector. But I will bias this distribution towards one direction, which I will call b. So I will add here some function of x dot b, so sum over I xi bi. Right? So this is a vector here. And I will normalize this vector, which is just actually setting the scale of the argument of phi, so it's no restriction at all. So the norm of b is going to be 1 in the following. So this distribution depends on b. And the problem I'm asking is the following. Let me assume I draw many samples, a certain number of samples from this distribution, and all the samples are independent from each other. I just extract them from this distribution here. And then I have my collection of data. I would like to infer the direction b. Okay? So it's a problem which appears in many contexts. And probably one of the most known contexts is the one where the function phi of u is quadratic. Let's say it's a, which is a positive coefficient, times u squared over 2. Then in that case, you see that since phi is quadratic, then phi of this dot product is going to be a quadratic function of the axis. So what I get is just a multivariate Gaussian distribution again, right? So in that case, what I get is that rho is multivariate Gaussian. And then the average value of the xi, the mean values are equal to 0. So everything is characterized only by the covariance matrix xi xj. So I keep to the physics notation with the brackets, which is simply the inverse of the identity matrix coming from this part, minus a times b transpose here, the projector along the b vector, minus 1 element ij. Right? And this matrix has all eigenvalues equal to 1, except one eigenvalue along the b eigenvector. And if you compute the inverse, what you get is simply the identity matrix plus a over 1 minus a times bi bj. So you see this makes sense only if A is smaller than 1, otherwise this quadratic form is not definitely negative, so the measure is not defined. Okay? So what that means is that, in principle, if I look at my cloud of points, this is a drawing I have already done several times, so in the x direction, then there will be an important direction which is B. So this is x1, x2. Then this cloud of points will be elongated here, if A is positive, with a typical elongation which is 1 over the square root of 1 minus A, while over all the other direction you get a 1, typically for the standard deviation, right? So now if you have an enormous number of points that you draw from this distribution, it will be easy, right, to find this direction doing principal component analysis. Right, if you have an enormous, your number of points P that you extract is very large compared to N, the question is whether it's easy to do when P is of the order of N, and that's a question that many people have studied in statistics, right? But you see, more generally, phi is not necessarily a quadratic potential in U. It can be any kind of function, and I'm interested in any kind of function. So I can have phi of U here, which can be like A over 2U squared. That would be the quadratic case. But I can have some non-even terms, powers of U. So for instance, BU. So it will push in one direction. You know, so I will bias here the distribution of the x's which have a positive dot product with B if my small b coefficient is positive, for instance. I can have also non-analytic terms. So C absolute value of U. I can have cubic term. You can imagine whatever you want, right? Any kind of phi function you can think of. Okay, so this is how I generate the data. I just generate independent samples from the distribution, and then the problem, obviously, of interest is to infer B. So let me write the posterior distribution. So given B, I will generate a lot of data, x mu's, with mu going from 1 to P. And then the question is, can I infer some B tilde? And I would like to know whether it's close or not to the ground truth B, right? That's a
maybe worth making a connection to what Mark was saying at the end, which is the same problem essentially.
Okay, very good. Yeah, I don't know, you want to...
Yeah, so I mean, just to make a connection with the last lecture of Mark when he was talking about addiction learning in the low rank case.
Yes.
So basically, it
exactly.
corresponds to this problem in the case when the rank is 1. And Mark had, in a sense, a matrix F multiplied by matrix X. So it is as if the F was the B here, and his X would just be Gaussian.
Yes.
And in the formulation that Rémi is giving, the Gaussian is just integrated over. So it's essentially the same problem.
Yes.
So Mark now explained us how to solve it using the approximate message passing and this type of algorithms. And Rémi goes towards the replica. So that's two different, but going to the same solution, compatible methods of solving.
I fully agree. Okay. Okay, so if we look at the posterior distribution over B tilde, so I will use this posterior, P posterior. Given the data, then this will be proportional to the prior of the B tilde, and the only prior I have here is that I would like to have the unit norm. So B tilde is on the n-dimensional hypersphere of radius 1. So I will have delta of B tilde squared minus 1. And then I have the likelihood here, which is just the product, or let's say the exponential of the sum of the mu phi of B tilde dot x mu. Okay? And mu is going from 1 to P if I've got P samples. Okay, so now if I go back to the specific case of phi, of quadratic phi, you see that we end up with a model which is very close to the spherical spin glass we have been studying in the last 2 lectures. It's actually one specific case of it, right? So if I consider again phi of u equal to a over 2u squared, then you can just take this dot product squared, and you see that gives that the sum of the mu running from 1 to p of phi of b tilde x mu is going to be the sum over I and j. If I exchange the sum here inside, I mean the one defining the dot product and the one outside the phi, so it's double sum over I and j. I have a over 2 here in front, b tilde I wij, b tilde j, where this wij matrix is simply sum over mu x mu I, x mu j, from 1 to p, right? So from a formal point of view, it's exactly the same model as the model we treated in the last 2 lectures, right? The big difference is that the W matrix is not a GOE matrix as I considered before, where I had just independent elements which were just drawn from a Gaussian distribution. Now my distribution for this Wij matrix is more complicated, and this is exactly what Giulio introduced this morning. This is called a Wishart matrix, right? Essentially, it's kind of correlation matrix of the data, right? So, Wishart matrix. So it's random because my data points are random. So there is a specific distribution for this matrix, the Wishart ensemble. Not that in the case where A is equal to 0, then I have completely independent variables. Then this is exactly the Wishart matrix with the identity covariance matrix that Giulio introduced. When A is different from 0, so I draw here with a bias, right? Then it's not the covariance matrix of this distribution is not equal to the identity. It's slightly biased along B, and this is how I can actually hope to get back B from the data, right? So now there are 2 parameters which are important here. So one parameter in that case is A, the intensity of the bias, right, of phi, of the potential phi. The other parameter which is important is the ratio between the number of data points and the dimension n of the problem. And this, depending on these 2 parameters, there will be a phase diagram, and I may be in a region where it's possible to do the inference, or a region where it's not possible to do an inference. Okay, I'll come back to that later on. But in general, I can also have phi of u, which is completely different from the quadratic potential. Okay, so I won't do the replica calculation for this problem, but you can trust me, you can do it, and it's essentially the same calculation as the one we did yesterday, because it's the same model. The only difference is that the distribution of the quench variables is different from the one I had yesterday, right? But you can do exactly the same calculation. So this is done in a paper which I'm citing here by Ranman and collaborators. And I think it's JFIS A, 1996. And you can have a look at all the calculation. I just want to say what is different with respect to what I did yesterday, right? Very briefly, so that you will see why we can apply the same techniques. So when we do the average over the quench disorder to get this effective energy coupling the different replicas. So here we are talking about replicas of the B tilde vector, because this is the one we want like to infer, right? So what I call X yesterday is now B tilde, right? Okay, so we will have an effective energy coupling the different replicas of B tilde, and the other parameters which will come out are obviously the overlap, as usual, which are going to be the BA tilde B tilde B, where A and B are replica indices running from 1 to n. Okay, but then on top of that, since we have a bias in the distribution now towards the direction B, then we'll have a new parameter which will appear when you do the calculation, which is RA, which is simply B tilde A dot B, which is the ground truth direction. I mean, it's pretty obvious that that should appear, right? Because when I will average over the quench degrees of freedom, which are the axes, which is W, let's say the axis, then the distribution of the axis depends on B. So B will appear somewhere, and it appears through the dot product with the replicas. Okay? Is okay? Okay, so now this is obviously a bit more complicated than what I had yesterday because I didn't have the RAs. But it doesn't change much because the important thing, remember, once you have defined your QAB, we then went from the configuration of the vectors, the BTIL, to the space of overlaps of matrices QAB, right? And the important quantity I had to consider was the entropy of these matrices. So given the set of overlaps of dot product between my small n vectors, I wanted to know how many configurations of these vectors I could have with a fixed matrix of overlaps QAB. Remember this? And I told you it's easy to do. So we did the full calculation, and then we end up with 1/2 log of the determinant of QAB. And I told you we could have guessed that because fixing the QAB is the same thing as fixing the variance of a covariance matrix. So what you should get is the entropy of a Gaussian distribution. This is the one with maximal entropy. But here you see we still have a Gaussian distribution over the BTIL because we are fixing the covariance on the mean. And we know that the distribution with maximal entropy where you fix the means and you fix the covariance is still a Gaussian distribution. So again, we can do the calculation very easily and you find an entropy which is given by the log of a determinant of a matrix which depends on QAB, on RA and RB. Okay? So you can go to the paper to see the details. But, I mean, conceptually, it doesn't change anything. Okay, so I just want to sketch the results. Okay, so the outcome is a learning curve. So what you would like to know is how fast, or first, are you going to learn the direction, the true ground truth direction when you accumulate more and more data? And one way to see that is to look at this overlap here, right, and see how it grows with P, which is the number of data points. Okay? So essentially what you would like to be able to predict, and this is the outcome of a replica calculation, is as a function of the ratio P over n, which is the number of data points divided by n, so it's an intensive thing. So we are going at the double limit P going to infinity, n going to infinity, which is the same double limit for the Wishart matrices that Giulio talked about this morning. So at fixed alpha, both parameters go to infinity at fixed ratio. We like to see how the overlap between B and B tilde is going. And ideally, what we expect is something where, you know, for a large number of data points, so when alpha is large, we should be very close to 1. And then we don't know what is going to happen here, but we expect something like that, right? If we don't have enough data, we don't have any data, then certainly we don't know what is the direction, so R should be equal to 0. And then it should grow this way, right? That's a very reasonable guess. So the outcome of the calculation is actually saying that, okay, this may happen, but you may have a different scenario where there is a critical value of alpha, which I call alpha C, alpha critical, below which R is equal to 0. And then only above alpha C, when alpha is larger than alpha C, you will start inferring something about the true direction of B. So R will grow with some curve here and will reach 1 eventually when alpha is very large. So how do we decide whether we are in this scenario or that scenario, right? So what is very important and that pops out from the replica calculation is that it depends very much on this quantity, which I call U bar, which is the integral over U for minus infinity to plus infinity, exponential minus U squared over 2, plus phi of U times U. Some kind of average value of U with this measure. I mean, we can normalize, but it doesn't matter very much. And there might be two different cases. Either this quantity is equal to 0 or it's different from 0. Right? And these are the two interesting cases. And if we are in this case, then we'll be in type 1. So maybe I should use colors. It would be easier. So this is this case. Or if we are in that case, we are in this regime. I hope you can see the colors.
The red, yes.
I don't know whether the red you can see, but not the yellow or whatever. I may have a better yellow. Is it better? Okay, that's the yellow. That's a good yellow. Okay. Okay, so I just want to say just a few words about that and try to understand why we have this qualitative difference between the two cases, which is the interesting phenomenon, right? So let's try first to see the red case. So the red case is the easy one. That's a very nice one, right? And actually, we can say just a little bit more about that. So R is growing immediately as soon as alpha is different from 0. And then it reaches, so my drawing is not very nice here, not very precise. It reaches 1 as 1 minus a constant over alpha. That's a typical case for most potential V, but you can have some strange cases where for specific V's you will get a different scaling. But essentially, you reach 1, you know. It's not extremely fast, right? 1 over alpha is just an algebraic way of reaching. But yet you go to 1 as alpha goes to infinity. Okay, so what is the intuition behind the first case? Or maybe I should, yeah. Okay, so the intuition between the first case, behind the first case is that if phi of u, you see, essentially you will get this red, when phi of u is not an even function of u. So for instance, when I have this a over 2u squared, you will be in the yellow case, which is bad. But as soon as you have, oh, I erased that, but as soon as phi of u has some linear term, for instance, right, you will be in the red case. So what does that mean? It means that you have directly in your function, in your distribution of the data points, something which really pushes the, if you take a vector x, which is a line along B, in the same direction as B, it will have a higher probability that the same vector x with exactly the same norm, but in the opposite direction, right? So which means that if you look at the axis, you look at x1, x2, and 1, and you just do the average of these x's, they will point in the direction of B, right? And that you can do with very few data. So as soon as you have a little bit of data, you know, compared to n, then you will see immediately what is the direction of B. It won't be perfect, right? But you will have some idea about the direction of B, and this is why you can infer you have a non-zero R as soon as alpha is strictly positive. Okay? Now, what about the other case? So this other case is more interesting in some sense, and it was first, to my knowledge, reported in literature under the name of retarded learning. So it's a paper by Watkin and Nadar, 1994. So they coined this retarded learning because you see, I mean, it's a little bit counterintuitive that you need a minimal amount of data before you can actually say something about the direction B, right? And this minimal amount of data, alpha c, is a function of your potential phi, right? It's a non-trivial thing. Okay, so in the case, so I will be brief because I think Giulio is going to discuss this more tomorrow in your lecture, right? So just want to say that in the case of phi of u equal to a over 2u squared, then this is known to be true, right? And there is an alpha c which depends on a, with the formula that I won't give, so that there will be some suspense. You have to wait for tomorrow, okay? You will see, but the formula is actually very simple. It depends on a in a well-known case. And in fact, what that means from a practical point of view is that if you are below this threshold, so what does that mean? Suppose you have some data, and what do you see if you are there or you are there? Well, you do principal component analysis in order to find B, right? This is actually what you should do if you want to do maximum likelihood inference, because you have a multivariate Gaussian distribution here. And what you do is once you have your data points, is you compute the covariance matrix and you diagonalize it. And in principle, you would like to take the top eigenvector and say, okay, this is my guess for B, right? This is what PCA is about. The problem with that, if you look at the distribution of eigenvalues, then this distribution of eigenvalues is actually the distribution. So this is centered around 1 if you have a well-normalized your data. This is actually exactly the Marchenko-Pastor distribution that was introduced to you this morning. and is exactly the same distribution as for fully independent variables. So you can take data with b equals 0, so that is fully independent variables, so you would get exactly the same distribution when n and p go to infinity. So in this regime, if you take the top eigenvector, which is here, this is just noise. It has very, very little information about the true b, right? Now, what happens if you are in this regime? So this is this regime, right? And I use blue. This is what you get. Suppose now you are above this, so that you have enough data so that your ratio alpha over p is larger than, your ratio p over n is larger than alpha c. Then you get essentially the same distribution for, but the point is that now there will be one eigenvalue which is well above the bulk of a spectrum, right? It's very far away, so my drawing, maybe I should. It depends on the parameters, obviously, but it's here, it's far away. And the corresponding eigenvector has a non-zero dot product with B. So it really comes out from the bulk of a spectrum, right? And then in this regime, you can say something about the true direction B. Okay? So it's a well-known phase transition. And you will see all the details in this paper I mentioned, and also all the details about any kind of potential you can think of, right?
I have a question.
Yes?
About the red case.
Yes?
Is it that also in the red case, if I just did PCA, that I would also see a phase transition, even though the kind of Bayesian estimation?
In fact, in the red case, you already see the information from the means, essentially. You don't have to look at the variance.
Yes, PCA Piquet actually.
With Piquet also? Yes, you will see also something. Yes, I agree. So I agree.
A case where actually the U has a different prior than Gaussian and phi against the T squared. And then we also have a case like the red case, but PCA actually ignores it because in a sense is not able to see the pattern.
No, but I think you are right. So I will check more carefully in this case. So I guess you will see immediately something, but then at some point you see this phase. You should see this phase transition. Okay. So there might be a way. We have to see in the other parameters, but we should see the two phenomena, starting with some non-zero r, and then you should see above. You should be above this threshold. I will check that, but you are right.
Yeah, in this
Both
case, I'm sure of that. In your case,
Okay, I will check that. It's a very good question.
And maybe just a comment also to connect yesterday in the open problem session. I think Ben was asking about the emergence of the learning as some parameters are changing, and this is like one really nice example.
Yes, but you will do that in detail with Giulio tomorrow. Yes, you have.
Yes. Can I just ask? Suppose I tried to scale U bar and let it depend on P and N. Like, can I scale it in some ways so I see things between the yellow and the red curve? Like, let's say that U goes to 0 with P and N, but at some rate. Can I get like a curve that's between them?
So I'm not sure I understand. You want to infer also the norm of B tilde, or?
I mean, like, take your function phi.
Yes.
And let it depend on P and N.
Okay.
In such a way that U bar has some interesting behavior, so that maybe it very slowly goes to 0 in your thermodynamic limits. And I'm just wondering if you can get something between the red curve and the yellow curve.
Yeah, I mean, it's a little bit strange because in principle, phi, it's something which is a function for one data point. So if it depends on the number of data points, it's a bit strange in terms of, distribution of the data. But you could imagine a model where it depends on alpha, right? This is your idea?
Yeah, for instance, right.
Yeah, it depends on alpha, I don't know. But otherwise, if you take the B to 0, you will get curves going smoothly from red to
Yes,
yellow.
yes, for sure. Yes. Yes.
I see, it's just that simple. Just
Yeah.
thanks.
Okay, so how do we understand this qualitative change of behavior? And I just want to give a very unwavering argument as a kind of competition between energetic and entropic terms. But I think it's interesting because it makes more clear the generality of the phenomenon. So the hand-waving argument is the following. Okay, the quantity I'm interested in is R, which is the dot product between the true direction, the ground truth direction, and the one I'm inferring for the data. So essentially, I can imagine I'm focusing onto the posterior distribution of R, and then I'm trying to guess what are the kind of contribution I could get. Okay? So there are two effects which try to counterbalance themselves. One is that if I have a true direction, which is this one, the enormous majority of the vectors are just, in high dimensions, are just orthogonal to it, right? So there is a huge entropy at small r, and if I want, which is r equal to 0, and if I want to increase r and go to 1, then there are lesser and lesser vectors with increasing overlaps, right? So that means that I'm expecting, as n is large, some terms here which defines the entropy of vectors having overlap R with the ground truth direction, with true direction. And this function S of R, well, we can compute it. It's again 1/2 log of the square root of y minus r squared. But I mean, what is important is that it will have some value for r equal to 0, and then it decreases with r, and it does not depend on the sign of r, right? Because whether you go to the left or to, I mean, it's exactly the same thing to go to negative r to be, suppose you are orthogonal, so r is equal to 0, you can increase this or decrease it, right? And then the entropy is the same. The direction here has absolutely no meaning, right? So you would expect that there will be a first term, which is S2R squared, if you do the expansion plus other terms of higher orders, where S2 is positive and S0 is some number that I don't care about. Is it okay? So that's the entropic terms. What about the energetic terms? I mean, the more data I have, I accumulate, the better I should be, and you know, in terms of trying to get a high value of R. So I'm expecting here to multiply this prior distribution, which is just something about, you know, the full possibilities of R values, by something which would decay exponentially with the number of samples I have, so that is P, times some effective energy E, which depends on R. Right? Very hand-waving argument. And E of R, again, should have some expansion here. So it could be E0 minus E1R minus E2R squared, and so on, right? And I put the minus sign here because I'm expecting E1 to be positive, which means that if I, by chance, I guess the right direction, so R is increasing, this effective energy of a sample, they should decrease, right? Because it's a good situation, so that should increase my posterior probability for R, right? Okay, so P is alpha n. And now I will just maximize this over R to find where is the best value, the most likely value for R. So I am doing just a maximum over R of S0 minus S2R squared minus alpha E0 minus E1R minus E2R squared, and so on. I'm neglecting all the higher powers. Okay, so I'm starting with alpha. Let's start with alpha equal to 0. If alpha equal to 0, you don't have this term, and the maximum is obviously in R equals to 0, but for entropic reason, right? So we start our curve like this. So I'm here, starting point. Now let's assume that alpha is not equal to 0 anymore, but it's very small. And you see, there are two situations. Either E1 is equal to 0, or it's not equal to 0. So suppose E1 is not equal to 0, so I get a term which is minus S2R squared plus alpha E1R. And I can neglect this term because R is very small. I'm starting from 0, so it's very small. So, and then if I differentiate this to get the maximum, I get minus 2 S2R plus alpha E1 should be equal to 0. That means that R is going to be so it's alpha E1 over 2S2.
So you are plugging the argmax?
I'm plugging what?
The argmax of the argument of the maximum.
Yes, exactly. Okay? So you see, in that case, for small alpha, then I get a linear term in alpha for R. Is it okay? That's a situation where E1 is different from 0, so that was my red case. But you can be in a situation where E1 is equal to 0, right? If there is no bias between positive or negative R. And in that case, then I have to pick up the second term, because this one is disappearing. And the second term is E2 R squared. And now you see exactly what is going on. You have a quadratic term with a negative sign here, and a quadratic term with a positive sign here. So when alpha is small, this one is winning, and the maximum is in R equal to 0. And when alpha is such that the alpha E2 is equal to S2, then you will start pick up and have a non-zero value for R. And that gives the situation where you have a critical alpha C here, which is the ratio of E2 over S2, something like that, right? Sorry, it's S2 over E2. And then something will happen which depends on the higher powers of R. Okay? So I think it's nice because it gives you a very hand-waving argument to understand why you can get these two scenarios, depending on whether you have a linear terms or not in this effective term. Okay. So I think I will end up here for this first part. So we'll go back to unsupervised learning on Monday. And then I would like to start the supervising. So it's always the same problem. I'm trying to infer a direction in a very high dimensional space, but I would like to do it from a classification point of view using, so today perceptrons, which are very simple single layer networks, and then tomorrow morning using 2-layer networks, okay, which are more complicated, and we'll see the structure of a space of solution, how they differ when you have hidden units. Is it okay? Canaries? Okay. Okay, so the problem I would like to look at now is how to do supervised learning of a direction. And I will do it first with a very simple linear classifier. Okay, so suppose I have a set of data, which are again some vectors, x mu, and some outputs, y mu. And I will, for simplicity, in the first time, consider binary outputs, which means I have only two classes, plus or minus 1, which is a setting that was already presented, I think, by Mark at some point in his first lecture, right? So if we want to do classification, then we are assuming that there is some underlying rule that actually associates y to x. So there should be some hidden function. By hidden, I mean unknown. But this is exactly what we would like to approximate. Function, which is actually defining y as a function of x, right? And this is what we would like to guess from data points. So on these data points here, and mu is running from 1 to p, and the vectors here are in dimension n. Always the same setting. Okay, so I will, in the first time, just to make our life a little bit simpler in terms of calculation, forget about this thing here and assume that the y mu are purely random and not associated to the axis, which is not the interesting case, but it's actually a good null model where you have no structure in the data, and you would like to see if your classifier is able to learn something or not, right? And when it stops learning, maybe it's the minimal amount of data you need in order to avoid overfitting, right? You can see it this way. So I will first forget about that, and then once we have understood what is going on, I will introduce back this function, which is the interesting case, right? Okay, so we will use a classifier, so linear classifier, which is just a perceptron. So the architecture is very simple. You have all your input units here, x1 up to xn. Then the output unit is computed as the sum here. It's a sum of the input times some coefficients. And then this can be compared to some threshold, which I will fix to 0 for simplicity. And then I take the sign of this. And this is my prediction for the output here, right? Okay, so I have some samples that I will try. So that gives me a set of constraints on the vector j's of coefficients. And I would like to know what are the possible solutions. And if there are a maximum number of samples, I can classify even if they have no structure. And how that depends on the number of data points and so on. Okay. Okay, so just to simplify a little bit the notation, since y is actually plus or minus 1, I can always put the y here. So I will multiply by y on both sides. And that is equivalent to 1 equal to the sine of y j dot x. Or let's say j dot yx. So I can forget about y and x, and I will simply define this vector here, psi. Okay? So this is equivalent to having a j which has a dot product which is positive. And you say that actually the classification of my xy pair is correct if j dot psi is positive, right? So being positive is actually a very fragile property, because I can actually maybe change a little bit my inputs, and then it can change the sign of this dot product. So I will try to impose something a little bit stronger as a condition. I don't want the dot product to be positive. I want the dot product to be larger than some number which is away from 0. So I will introduce some condition here, kappa, which is called the stability. It's very similar to the margin that people use in support vector machines. It's exactly the same thing, actually. Okay, so my constraints are that this should be true for all mu's, right? I would like to find a vector j, such that j dot psi mu is larger than kappa for all mu's, so for all my pairs of input-outputs. Obviously, that doesn't say much if I do it this way, because it doesn't depend on kappa, because I can always rescale j by some factor, and then I can make kappa as large as I want, right, if I have a solution. So if I want to make this meaningful, I have to impose something on the norm of j. So I will impose, for instance, that j squared is equal to n. And now I'm asking the question, can I find solution to this set of inequalities on the hypersphere of radius square root of n? Okay? And you guess that if the number p of conditions here is going to be small, then there will be probably many solutions, unless I'm very unlucky with opposite psi mu's, right? And if this is increasing, at some point, maybe it will be just impossible to find these solutions. Okay, so this is actually something which, in terms of geometry, is very simple, and there is a huge difference with the multi-layer networks we will see tomorrow morning, because the domain of solutions here is convex. So if you assume that kappa here is positive, and I will come back to this, it's a crucial assumption. If you assume it's positive, right, then, and it's reasonable from this thing here, then the domain is convex. And you can check that very easily. Imagine you have a first solution, J1, which is solution of this on the hypersphere. You take J2, another solution, and then you look at the geodesic between J1 and J2 on the hypersphere, and you can see that all the points in between are satisfying these constraints. That is not true if kappa is negative. So that means the space of solution is convex. and it has some kind of simple shape, right? So one way to picture that is that suppose I have, this is my hypersphere represented as a square on the blackboard, but you should think about it as the hypersphere. So this is the set of all possible j's. And in fact, each time you add one constraint, you cut your hypersphere by a hyperplane which is orthogonal to psi1, for instance, and only one half of a hypersphere is allowed for the solution. Then you have another hyperplane orthogonal to psi2. So you have the intersection of a half hyperspheres, okay? And you end up with some domains here, which will be delimited by some hyperplanes. And this is the feasible set, or let's say the set of solution, right, in the J space. And we guess that at the beginning, if we have no constraint, we have a huge set of solutions, and in the whole hypersphere is okay. And as we increase the number of hyperplanes, it shrinks, and at some point, maybe it will become empty, right? Of course, it will depend on the particular set of samples we have, a set of data. But maybe there might be some typical features which depend only on the ratio between the number of data and the dimension of a problem. Yes?
Do you want to have j.psi order 1?
Sorry?
j.psi.
Yeah, so here, yes, you are right. I should mention how we do that. So if I normalize, so what is the scale of kappa with n? That's a good thing. Okay, so I should define my things here. So I will assume that the x mu's also, they have components xi mu, which are plus or minus 1 with probability 1/2. So I'm taking the most boring data you can think of. Everything is equally likely, 1/2 for plus or minus 1. No structure, nothing, no rule. It's really the most boring null model you can think of, right? But I think it's interesting to start with. And then I tell you what happens when you put structure in the data. Okay, so that means that this is a vector of square norm equal to n. This one is square norm equal to n, right? So if we impose this thing here to be of the order of n, it's a very strong requirement. J should have a dot product which is, it's very much aligned. So I will relax this, and I will simply impose that this divided by the square root of n should be larger than kappa, which is of the order 1 when n is large, right? So, if you take two random vectors on the hypersphere, essentially, then this thing is of the order of square root of n, right? So we don't have to work too much in order to have something of the order something which is of the order 1 for the ratio. Otherwise, it would be a very strong constraint, and you could not accommodate many of them. Only a finite number compared to n. Okay? So I want to solve this problem with replicas. In fact, we have everything to do so. And I will just show you briefly how it's exactly the same kind of problem we have looked at so far. And if you want more details about the calculation, you should refer to the original papers by Elizabeth Garner and Bernard Derrida from the end of the 80s, where this calculation was done first. Okay, so if I pick up two solutions in my feasible set here, so for instance, one solution here, another one, I just pick up them randomly. So first of all, from an algorithmic point of view, it's easy to solve this problem, right? There are many algorithms which are able to find solutions if they exist. The first algorithm to do that was the perceptron algorithm, learning algorithm, from I think the end of the 50s, beginning of 60s, I don't remember. You can use, very optimized SVM algorithm, which are just convex optimization algorithm under a set of linear constraints, and this is very efficient to find in polynomial time solutions. So you can find solutions to this when they exist, obviously. Okay, so now you pick up two solutions, let's say J and J prime, and I'm asking what is the similarity between these things here, right? That's the usual question you can ask with replicas, and there are not so many questions you can ask. So I will define this thing here, Q, which is the overlap between these replicas, right? So Q is going to tell me something about the size of this domain. If Q is going to 1, it means my domain is shrinking. So by Q, I mean j dot j prime over n. If Q is equal to 0, that means my domain is really enormous because everything can be inside the domain. Most of the vectors will be inside, right? Okay, so what I'm expecting is that Q, which measures the size of this domain, is going to be an increasing function of alpha, which is P over n. So again, this is my guess. Alpha, which is the number of constraints divided by the number of degrees of freedom. And if I have a measure of Q, so if I start with no constraint, then 2 random vectors on the hypersphere, they are orthogonal, so Q will be 0. And as I increase alpha, this thing should increase, and it will hit 1 at some particular value of alpha, which I will call the critical value of alpha, which is the maximal number of constraints per degrees of freedom that my perceptron is able to classify, right? So if I have more than alpha c times n patterns, my perceptron will not be able to classify them, let's say with high probability when n goes to infinity. Okay? So I would like to find this alpha c at which Q is going to hit 1. Okay, so the fact that P should be of the order of n is the right regime, that is pretty obvious, right? You see, the thing you can do, worst case, is say, okay, instead of inequalities, you put equalities, and that you can always do if alpha is smaller than 1. So alpha c should be at least equal to 1. Probably it's going to be better. Okay, so let me compute what the equivalent of z, which is a function of our data, psi mu, which is going to be, as in the spherical model we had yesterday, the integral over the vectors which are on the hypersphere, and that satisfied all the conditions. So I will have a product of a mu from 1 to p of the condition. That means, and so I introduce here the Heaviside function. So theta of u is simply 1 if u is positive and 0 if u is negative. Okay, so I can put just to be defined, j dot psi mu square root of n minus kappa. Okay, so I have the whole hypersphere, and I put a constraint that all these quantities, all these dot products should be larger than kappa. And I would like to compute that, right? So this is a measure of the volume on the hypersphere of the set of solutions. Okay. So you know how to deal with that with replicas. So what we are going to do is just repeat the same procedure as usual. We are trying to now to look at different replicas of these thermal variables, which actually see the same quench disorder, which are the data, and try to see how they get in interaction together when we average over the quenched data, right? It's always the same strategy as we have already done. So I will do z to the n, and average here, and you see that you will get some dg product over a running from 1 to n, dga. Then we have the product over a of the conditions to be on the hypersphere, squared minus n. And then we get the interesting part, which is a product over a, product over mu of this theta function, ja dot psi mu over square root of n minus kappa. And this should be, I put here the average here, that's the average over the quenched data. Okay, so first of all, so let's try to compute this average, and you will see it's not actually so difficult. So first of all, since all my data points in my very simple model here, they are just independent from each other, the average of a product of a mu is just the product of the averages. So I will simply, so let me just commute mu on A, and then the average of a product is just the product of the averages. Is it okay for everybody? Yes? So I can do that here. So I have a product of the averages that couples all the replicas for the same mu, right? And since the mu, they are also independently drawn, I mean, with the same distribution for each mu, that means I have to compute a single average and put it to the power p. Okay. So now, what is this thing here? Okay, so let's look at this quantity here. This quantity, which I will call delta A. It's just the dot product between the replica number A and the pattern. And I can forget about the mu index here because they are all equivalent in statistical terms. So what is delta A? Delta A is a dot product. So that means it's a sum of many, many terms, right? So these psi are random, right? So if I sum many, many random terms like that, what I will end up is a distribution of the delta A's, and that is for A running to 1 to n, which is a multivariate Gaussian distribution. Again, it's just the central limit theorem associated to n, small n variables, right? When I do capital N very large. At fixed small n. So that means the distribution of this thing is going to be Gaussian. So I just have to compute the mean and the variance in order to fully characterize the distribution. So what is the average value of delta A? Well, since the psi I are plus or minus 1 with pretty 1/2, this is 0 for the mean. And if I want to compute the variance, I just copy that twice and multiply, and then I average. Times the same thing with the B. And let me do the average of that. So I'm doing the average over the pattern psi. And you see that I have psi I times psi j. And they are independent components of the same pattern if I is different from j. And they are equal if I is equal to j. And this is 1. So I end up that the fact that psi I psi j is simply delta ij. So I end up with something very simple. It's simply 1 over n sum over I, J, I, A, J, I, B, which is the QAB, the standard overlap that you have heard again and again about, right? So it tells you that the distribution here is actually fully determined by the overlap between the different replicas of the perceptron vector. Okay, so once we have that, it's easy to write this thing here inside the bracket, and then we will elevate it to the power p. So you see that this product of A of the thetas and so on, of delta A minus k, this thing here, well, I can replace the average over the quench disorder by the average over this Gaussian distribution, right? So it will be simply the integral, so it's a multiple integral, a small n-dimensional integral, from each delta runs from kappa to infinity, and I put here the Gaussian distribution, exponential minus 1/2, sum of the A and B, delta A times the inverse of the covariance, so Q minus 1 AB, delta B. And that has to be normalized by I have to normalize the distribution. So there should be 2 to the pi, 2 pi to the n over 2 times the square root of the determinant of Q. So remember what we had yesterday for the spherical spin glass? What did we have at this? So this is the effective energy. For the spherical spin glass, we had, so I just write it as a reminder. For the spherical spin glass, we had something simpler. We had exponential. Sum over AB, I think there was a sigma squared over 4, if I remember, QAB squared. Right? That was nice, simple. Here it's a bit more ugly, but formally, conceptually, it's the same thing. It's a function of a QAB matrix. That's what matters. It was a nice function, now it's an ugly function, but that's it. It's a function. Right? So which means that everything we did yesterday, you can actually redo. And I won't redo all the calculation because it's just boring, right? But you have all the tools to do exactly all the calculations you want. Okay, so where do we end up? That I should not use. We end up in the fact that this nth power of the volume here is going to be the integral over the QAB matrix, dQAB, the overlap matrix, times, okay, what? So we have the effective energy, which is this thing here. So the whole thing here, that is, this thing here is an exponential of minus the effective energy, G1 up to Gn. Okay? And this whole thing should be to the power P. So we have exponential minus alpha n times the effective energy, which is a function of a QAB matrix, which is written here. And then when we go from the integral over the replicas of the perceptron vectors to the integral over the overlaps, we have again the entropy of a QAB to take into account. And that is again the same thing as we computed yesterday. This is n times the entropy. And this entropy, if you remember, that is simply 1/2 the log of the determinant of this matrix. Is it okay? Yes? So exactly the same calculation as yesterday, except that this effective energy is not as nice as the trace of Q squared. It's a complicated function, which actually is interesting because it does not depend only on the eigenvalues of Q. Now it's more complicated, right? But it's exactly the same calculation. So now I should ask you how much you are bored with the replica calculation. So I can give you the outcome, or I can do a little bit more of this and do the n going to 0 limit. You can be frank. Okay?
I think the step about how you go with n to 0 is useful. It's less obvious.
Okay. So let's do the useful boring step. Okay? So let's do that. No, it's okay. Okay, let's do it. I agree. Okay, so I will do it, but I will simplify a little bit my life by doing a calculation only when Q is close to 1. Okay? So I will simplify my life by doing two things. One thing I said you should never do yesterday. I was asked a question. I don't remember who asked the question. So first I will do the ansatz. Okay, that QAB is a replica symmetric matrix. So I can erase here. Okay, so we are looking for QAB as usual. We should enjoy that because from tomorrow morning, 8:45, it won't work anymore. So, okay, so it's nice. So I will use that, put it here inside my expression that I erased, but you have it on your notes, okay? And then do the small n going to 0 limit. In principle, as I told you yesterday, you shouldn't do that. You should do the saddle point here, right? The optimization equation, then do the ansatz, okay? Because then this way you can compute the Hessian, you can do a lot of things. Otherwise, you cannot do that. But just to spare time, I will do it this way, which is dirty but quicker. Okay, so with this ansatz, first the entropy S of Q that we already computed. So I'm just writing again the expression. This is 1/2 log of, so we just have to diagonalize the matrix. So one eigenvalue is this one. And then I have one eigenvalue, which is actually n minus 1 times the degenerate, which is simply 1 minus q. Okay, so remember what we want to do is to find where this volume shrinks and goes to 0 and q goes to 1. This is going to determine the maximal ratio alpha. So I will forget about the full learning curve, which is q as a function of alpha. I will focus only on the value of alpha c, just to have the calculation a little bit shorter, right? So I will assume that q is actually very close to 1. So I will assume that q is 1 minus epsilon, and I will take only the leading term in epsilon, whatever they are, which means order 1 over epsilon, or sometimes a little bit bigger, as you will see. Okay, but of course you can do the calculation for the full q even when q is small, but if we want to get alpha c, this is the only thing we need. Okay, so in that case, if q is 1 minus epsilon, and epsilon is small, you can just replace it here, and you find that this is n over 2 epsilon plus n O of log epsilon. So I'm going to neglect all the terms which are of the order of log epsilon. So we are very close to a point-like domain. Okay, so this is one term here. That's nice. Now I have to deal with this one, which is not nice. I have to deal with this one, which is, remember what it is? This is the product from kappa to infinity, d delta a over square root of 2 pi. I have exponential minus 1/2 delta a q minus 1 ab delta b. This is sum over a and b. And then there is a square root of that q here. So the square root of that q we already have from there, because here this is 1/2 of log that q. So this is just the exponential of that. And for small n, you see that is going to be, if you take the exponential of this for small n, this is just 1 plus n over 2 epsilon. So just to be sure there is no misunderstanding in the limits, you should do first capital N to infinity, then you should do small n to 0, and then you should do small epsilon to 0. Okay? And that has a meaning. So here that means I always picking up only the terms which are linear in n. Okay, that we know, but then we have these ugly things to compute. So let's look at this matrix Q minus 1. Q minus 1 actually gave you the expression yesterday. Remember? Yes? So if you just look at Q minus 1, you can pick up the formulas I gave you yesterday, and you can check that this is equal to the identity matrix over epsilon. And I have elements out of the, so you take the full matrix with minus 1 over epsilon squared everywhere, and you add the 1 over epsilon times the identity. This is true for small epsilon. So this is the dominant order in very small epsilon. Okay. So I can plug this in here in the quadratic form. And if I do that, this is exponential minus 1 over 2 epsilon sum over a running from 1 to n delta a squared. And then I have plus 1 over 2 epsilon squared sum over a delta a squared. So be careful here. We have the sum of the square elements, and here we have the square of the sum. So I will give you the interpretation of this, right? So that you get some intuition about what we get at. But let's finish the calculation. Okay, so the plus here is just a product of the exponential. And now, what I would like to do is to do this small n going to 0, right? And that is nice because here I have n independent variables, and so this is just a product of integrals. What is bad is this one because they get all coupled. So I will use a trick, which is a decoupling trick. I will just introduce a dummy variable, which is a Gaussian variable, which will allow me to linearize this. It's a well-known trick. So I will just write this as an integral over some variables, which is a Gaussian variable. I mean, minus infinity plus z over epsilon times sum over a delta a. In fact, if you do the integration of the z, you will get exactly this term, right? Now it's nice. Of course, I have a price to pay, which is this new variable I have to integrate over. But now my replicas are uncoupled, so I will be able to integrate over them and do the small n going to 0 limit, which is very easy. Okay, so it's going fast. Yeah, so the exponential of minus the effective energy, which is a function of epsilon now, is this integral here. So I have the integral of z, right? And then I will collect all the integrals over delta A, and you see, since they are all independent, and now, so it's the same thing as a single integral of a single delta to the power small n, right? So this is an integral of a delta, 2 pi, running from kappa to infinity. Then I have a minus delta squared over 2 epsilon, plus z delta over epsilon. And the whole thing is to the power n. And then I have this 1 over 1 plus n over 2 epsilon, which comes from the square root of a determinant. Okay? Almost done. So now n is small. So this whole thing here, so something to the power n, is exponential n times the log of this, and then you expand to first order in n. So it's 1 plus n times the log. So the whole thing here is simply 1 plus n times the log of the integral of a kappa delta, infinity, d delta over square root of pi, exponential minus delta squared over 2 epsilon, plus z delta over epsilon. Okay, so now since n is small, I can put this at the numerator with a minus sign. And if you do the integration of the z of a constant, this is 1, because this is the normalized integral. So you get 1 minus n over 2 epsilon plus n dz log of this integral here. Okay, so let's do the integral now, and I will do something. You know what? I will like to complete this this square here. You see, this is minus, so I have minus delta square over 2 epsilon plus twice the delta over 2 epsilon. I will like to complete it to get a full square. So I will do a minus z squared over 2 epsilon here, if I do that. With the log, actually, if you compute the log of this, so this is minus z squared over 2 epsilon. With the integral, this is exactly this thing here, right? So I just get rid of that. And now I have something which is nice. I get this is exponential minus delta minus z squared over 2 epsilon. So we'll interpret this soon. But let's finish the calculation. We are almost there. Okay, so now I have to compute this integral here, and this integral of a delta depends on z, because delta is pinned around z with some variance here, which is epsilon, right? So now the question is, when epsilon is going to be very small, we have to see what are the values of delta which are dominating the integral and giving the most important contribution to the integral, right? So clearly we would like delta to be close to z, because this is the only point where this thing is of the order 1, otherwise it's very small. So delta can be equal to z, that's nice, but only if z is larger than kappa, otherwise it cannot be, right? So you see that for all the z's which are actually larger than kappa, the integral here will be very close to 1 times some Gaussian correction of the order square root of epsilon. Okay? When we take the log, it will be of the order log of epsilon. I don't care about log of epsilon. I'm neglecting all these terms here. They are too small, right? So the only terms which are interesting is when z is actually smaller than kappa. Then that's really bad because delta would like to be as close as possible to z, but it cannot go lower than kappa, so it will get stuck in kappa. So for z smaller than kappa, I will get this term here replaced with, where I replace delta by kappa, plus times some corrections, which depends on the integral here, which are of the order of epsilon. Take the log. We don't care. It's log of epsilon. So I'm saying that when this epsilon is very close, it's very small, this is 1 plus n times the integral over z running from minus infinity to kappa, exponential minus z squared, times the log of this stuff taken in delta equal to kappa. So this is times minus 1 over 2 epsilon delta, kappa minus c, plus terms of the order log of epsilon. You agree with that? A little bit unconventional calculation, but that's the way it is, right? Then we are done. We are done because we have finished the calculation. So we have a term which is order 1 over epsilon times n, and we have this term here, which is also the same thing. Now, if you put back everything in the calculation of z to the n, we have finished. So that I erased, but so I would like to finish that and explain and give some intuition about this strange calculation here. So we finish with z to the n, which is going to be exponential of n times. So we had this, so there is a small n here, 1 over 2 epsilon, which come from the entropic term. There was the log of, you remember, that was the n over 2 epsilon, minus, so there was the exponential minus p times the effective energy. So the p, I already factor out n, so there would be an alpha, p is alpha n, times this thing here, which is n. And there was a minus effective energy, so it would be a plus, because it's this to the p, right? So I don't have. And I have the integral of z.
Small n is already outside.
Sorry, you are right. So kappa, so that runs from minus infinity to kappa. So I have a z minus kappa squared. And I think there should be a minus 1 over 2 epsilon here. So maybe I can just factor it out. 1 minus alpha times this. Plus terms here of the order of log epsilon, right? Which I completely neglected all over the place. Okay, so now you see what is going to happen. If the term within parentheses is positive, then epsilon, actually, when epsilon is small, this is really big, right? This is huge. So that means, so is it possible that the volume is actually huge? No, it's bounded by the volume of a hypersphere. It means that my assumption that epsilon was very small is not correct, right? Now, when the terms here within bracket becomes negative, then when epsilon is going to be very small, it gets to minus infinity, right? So you see the only regime where actually epsilon very small makes sense is when the terms here is very close to 0. And the value of alpha, which actually cancels the terms, is actually the critical capacity. So if you wanted to do it very cleanly, you should compute all the terms here and do the maximization over epsilon, right? But I cannot do that because I've neglected all the terms. But this is sufficient to get the critical capacity. So alpha c is simply 1 over the integral from minus infinity to kappa. So it's a result which was first obtained by Garner in I think 87 or 88. 88, I think. I don't remember. And it's a very nice result, which was a generalization. So the only case which was known at that time was the case kappa equal to 0 when you impose only the positivity. It was known from the 60s and there is a very nice argument by Cover, which gave the capacity of this linear classifier. And you see for kappa equal to 0, actually, this is 2. But in general, when kappa is larger than 0, then of course you have stronger constraints, so the capacity decreases. So you can plot this as a function of kappa, or if you prefer to put alpha here, the 2 kappa here, and there is a curve here which does something like that. And which goes to higher value of alpha c, where kappa is negative. Okay? So very nice thing. So I wish I had done this earlier, but I couldn't do it. So there are many, many extensions, so I will be very fast in the extensions. This has been extended in all the possible ways you can think of. So, and probably even more. So for instance, instead of having continuous J's, you can have restricted J's. So you can say my J's are bounded. So an interesting case is when the J's are all positive. It's interesting because it's a biological constraint. They're slow in neurons, you know, they can have only, fixed sign interactions. You can have J equal to plus minus 1. You can have a lot of constraints. You can have constraints on the statistics of the data. Instead of having plus 1 or minus 1 with probability 1/2, you can say, well, you can go to 0, 1, which is a bit more realistic from a neural point of view, but that doesn't change much. But you can say, okay, maybe the 1s are much more likely than the minus 1. You put biases, right? You can do that. You can also have more structured data. Interesting. So you say my patterns are not independent anymore. Psi mu and psi mu prime are correlated. You can say, okay, my patterns are independent, but the components within the patterns are correlated. Psi I and psi j are correlated. That's interesting. I'd like to come back to this tomorrow. You can do extension not to linear classifier, but to recurrent neural networks. So it's exactly the same thing. So recurrent neural networks, you say, okay, instead of having classification, which is mapping x's onto output y, you can say, okay, I will map x to one of the components of x. It's called a heteroassociation. It's just a specific case, right? A particular case. So suppose, for instance, you have a recurrent neural network. So you have a lot of units like that. They interact through some Jij. And you have a dynamics, for instance, that the dynamics of your neuron at time t plus 1 is simply the sine of its input computed from the activity of a network at time t. There might be some threshold, but forget about the threshold for a moment, right? And then you say, okay, that's nice. I would like to embed in the network some memories, which are fixed configurations of activities, right? And this is essentially a version of a Hopfield model where you don't fix a priori the Jij, but you look for the best possible Jij. You don't say the Jij are the Hebb rule, but you know they could be anything. So in that case, you want, for instance, the Muse configuration to satisfy this constraint. And that should be true for all I and all Muse. But you see, this is just, if you look at the row number I of this matrix, this is just a perceptron problem where the output corresponding to the input pattern x mu is y mu is simply the ith component of x mu. So it's exactly what we have done. So if you want to solve this problem, you have the same capacity as this one. It becomes interesting if you put constraints, for instance, between Jij and Jji. And there are nice works about that, where actually the capacity can change and it becomes very difficult. Still have 5 minutes. Okay, so even more extensions. Yes?
So earlier you said that when k goes to negative numbers, we
yes,
have different spacing?
Yes, the curve here is wrong. I want to come to that. I plotted it, but it's wrong. Okay, but it's fine. Okay, so a case I would like to discuss tomorrow if we have time is that when the psi mu, actually the patterns are embedded in low dimensional manifolds. That's an interesting case. You can imagine you have your patterns, n-dimensional patterns, but they're actually described, you know, they have the psi mu would be something like some phi here. So this is in n dimension of some coordinate x mu here, which is in d dimension, much smaller than n. So you draw randomly your points on your manifold that defines very big vectors, and then you would like to store them, to classify them. So that's an interesting case. And there are many other cases probably I'm forgetting. Yes, obviously I'm forgetting also actually the motivation. The motivation was what happens when the outputs, y mu, are function of the x mu. They are not just random, right? So I think I will say something about that tomorrow, because I don't have time. The last thing I would like to say is about this part of the curve. Okay, so as I told you, what we should do in order to be sure, to understand whether this curve is meaningful or not, is at least a self-consistency check, which is whether the Hessian of this effective term, which is the entropy minus the effective energy, is well defined, right? We are looking for minimum, so I should make sure that all the eigenvalues are positive. It turns out that all the eigenvalues are positive on this curve, right? But one of them becomes negative here. So this thing is completely wrong, right? So this part here is completely wrong. So said this way, it's a little bit, abstract, but we can have actually some I think, intuitive grasp about what is going on from this very simple argument. I forgot to interpret the calculation I did. There was this strange calculation I did here. Remember, if z was smaller than kappa, then delta is stuck to kappa. If z is larger than kappa, then delta can be equal to z. What does that mean? So we can have some intuition about that. And then I think I will stop here and then see the application for this. So actually, it's easy to have some intuition about this calculation, understand where it comes from. Suppose you have already classified p patterns, and you have found a perceptron, which is doing a good job at classifying all your p patterns here, and this is your average thing, but actually, the domain of solution is this thing here, which is described by some overlap q, which is 1 minus epsilon. So you have already p pattern, p quenched patterns, right? Data points, and your set of solution is there. And of course, they all satisfy the condition that they should be, the dot product should be larger than kappa. So they all lie on this part of a cone. Now you arrive with a new pattern, you come with a new pattern number p+1, and you would like to classify it with your perceptron. So now you have a trade-off to realize between not going too far away from where you are, because you are constrained by the first p patterns, and the new one, which is whatever you can think of, right? So you see that there are two possibilities. There is the good possibility. It turns out your pattern, the new one, psi is here. That's nice because you can take j dot psi, it's already above kappa. So you are done. And that corresponds to the case where, so what is the famous z I had before? It's actually the dot product between this and this, which is just a random Gaussian variable. So in that case, the stability of this new pattern with j, you have nothing to adjust here, and delta will be equal to z. And it costs nothing in terms of volume of the z. It's very nice. In fact, all the part of the integral with z larger than kappa did not contribute to this expression. It's no cost. It's free to store this, to classify these patterns. But now you can be in a bad shape, in a bad situation, because your new psi is here, or it can be on the other side, right? It can be. Then z now is smaller than kappa. That is bad. You cannot change anything on a quench data point. What you have to do is to move your patterns here, right? So you move your weight vectors in order to try to increase the dot products and make it equal to kappa, right? And so you do that, and of course, that costs you a lot because there are less and less solutions as you move away from that. So the thing you do, which is minimal cost, is to have the dot product exactly equal to kappa. And that was the other case. Oh, I changed color. Okay? And that costs, and this is what is decreasing the volume. And you see the integral here with a minus sign. That's killing you, right? And these patterns are responsible for capacity. So now, and then I will conclude, is, okay, once we have understood that, so we see that we have nice quench data, which are actually lying inside the cone here. And we have the bad ones, which are really on the sides of the cones, right? They are called the support vectors in support vector machines. These are the support vectors, right? So now, if we look at these guys, you can say, how many bad guys do I have which are really satisfying the condition that this is equal to so for all the mu's which are on the side here, I should have this, right? So here you see I have inequalities of these ones. And it's much easier to satisfy an inequality than to satisfy an equality. So you can ask what is a fraction of the patterns, of the data points, which satisfies the equalities. And you know for sure that they cannot be larger than n, because we are in an n-dimensional space. So you can compute the fraction of these guys, multiply by p, and that should be smaller than n. That puts an upper bound over alpha, right? Is it clear? So that is easy to compute. So what is the probability that this is satisfied? Well, that's the probability that actually z was bigger than kappa. So the probability that z is smaller than kappa corresponds exactly to these things here. Okay? So the fraction of this guy, this is the integral of z from minus infinity to kappa. And if you multiply this by alpha n, which is p, that should be smaller than n. So that means that the whole thing should be smaller than 1. Okay? That should be true. Now you can plot the curve here and see what it gives, and you see that it does something like that. So that means your solution, replica symmetric solution, cannot be true here. It's wrong. It can be true here. In fact, it's true on this line here. It's perfect. But everywhere here in this region, it's completely wrong. You know, and it's a way to see actually the instability is somewhere here, right? So this region, you need an ansatz which is not replica symmetric. So we'll see tomorrow what kind of ansatz we can do and how it's connected to the nature of the repartition of the domains, right? And the fact that the domains of solution are not convex anymore, but it's full of small domains in all over the place, this is crucial for this instability here. Okay, so we stop here. Yes?
So in the previous case, was it obvious that at capacity Q should be 1?
In the previous case, you mean here?
Yeah.
I mean, my domain is shrinking.
But how do we know there's not, like, it shrinks, but there are two Q's which are, the two J's which are not the same.
Yeah, okay, you could be...
Take this offline.
Yeah, okay, very good. We can...